Hello students, this is Brock Skaggs, and I'm going to make this video showing you how to perform a kinematic analysis using SolidWorks Motion. And what the mechanism we're looking at is going to be this lazy tong mechanism you see in the top portion of your screen at this point. And so the lazy tong mechanism, if you haven't seen it operate before, I'll show you a short video here of the motion we're going to be looking at. And so you can see this kind of accordion style motion here that we have. And so what we're going to have is this slider on the left be the driving link, and then we're going to be wanting to know, okay, if I know the position, the velocity, and the acceleration with respect to time of the slider on the left, can I predict the position, velocity, and acceleration of the slider on the right side there? And what we're going to see is there's somewhat of an amplification that happens here with all of these links that are in between there. And so that's the motion we're hoping to achieve inside of our motion study today in this specific video. Then I'll make a second video showing how to compare those with the theoretical calculations. The theoretical calculations for this specific setup of the lazy tongs are going to be based off the equations that you're seeing right now in the screen. And so I just went through, basically I've developed equations relating position to velocity and acceleration there. And basically it's all going to be based upon us knowing the information about point A and trying to predict what happens at point B there. And so we'll be focused on these a little bit more in the second video. And so enough of this, let's go ahead and hop into SolidWorks. And so in SolidWorks I've already got the parts modeled. And so nothing too crazy here, very simple model here. The hold-to-hold distance of our short link here is 3 inches. The bigger link is a little bit longer, it's 6 inches there. And the hole in the middle is exactly at the midpoint there. And then I've also have a nice little slider that we can put on the ends there. And so nothing really big has happened at the part level, but we'll have to make a few comments about the assembly when we get through there. And so what I'm going to do is just start a basic assembly here. Make sure the units are IPS since everything else has been in inches for this model. And I'm going to go ahead and show these planes. And so I'll just go View Planes, and from the top I'll go and show the planes as well. And so one thing I'm going to do before I bring any parts into this assembly is create the fixed axis that I'm going to be basically building my model about. And so this fixed axis is right where the origin's at in the diagram you're seeing on the screen now. And so you've kind of got this fixed pin connection here, where that pin connection doesn't translate at all and everything's kind of built around it. And so how am I going to do that in SolidWorks is the question. Well, it's fairly easy. I don't really have to create much in the way of extra geometry in order to facilitate that. If I can get over to SolidWorks here. There we go. What I'm going to do is I'm going to use reference geometry for that. And so here's my reference geometry here, and really all I need is an axis. And so the axis, I'll use this two planes intersection, and so I'll select the top plane and the right plane here. And notice that makes a nice axis there that's running in the Z direction, which will work nicely for this fixed axis here. And so there's axis 1 there. And so I'll basically have most of my motioning happening basically parallel to the front plane here, and that's a nice perpendicular axis that I can have things rotate about. And so with that put in place, let's go ahead and bring some parts in. And so I'm going to get the Lazy Tongs link file and bring a copy of it in. Notice at this point it is fixed. That's what the F stands for next to the file name there when you first bring your initial part inside of an assembly in SolidWorks. And so what I need to do is float it. And so I'll just right click on the part itself and I'll transition it from fixed to float. And you can see the F turns to the minus sign there. One other thing I'm going to do is I'm going to show the temporary axes. And so I'm going to go up from view to temporary axes here. What that allows me to do is see these axes that are associated with these arc centers and the hole centers there. And so this guy should have 3 of them, one basically marking the center of each of the holes. And so with that put in place, we should be able to start mating this thing up to these planes and this axis 1. And the first thing I'll do is I'll go to mate, and I want to make sure that this axis here is coincident with my reference geometry axis. that allows this thing to do is, of course, rotate about that axis, but then it can also translate as well. And really, we're just interested in the rotation of it, not necessarily the translation along the axis. And so what I'll do is I'll go back to Mate. I'm going to select this front face of this link, select that front plane in order to kill that translation along the axis. And so now if I go to play with this, just putting it in ISO there, notice all I can do is have it rotate about that axis 1 that we created, which is exactly the motion that we're looking for. Here, when we actually run the model, it's not going to go through full 360-degree rotations, but it's just going to oscillate, which is exactly what we want. And so obviously we've got the first link in there. Now we just need to start adding more links. So I'm just going to hold the control key down, pull off of the icon on the tree structure here. I could have pulled off of the actual part geometry here in order to bring a copy of it in. And so what I'm going to do with this one is a very similar process. I'll select axis 1 and the center point. Or excuse me, not the center point, but the axis associated with the center of that hole. And then I'm going to select this back face and the front plane there and accept those inputs. And so what this allows me to do is have these two links, both of them attached to the front plane there. One's on one side, one's on the other, and then they should be able to rotate about it. And so what these two links represent, to get it back to the diagram here, is this link here and this link right here. And so let's go ahead and build the left side of this first. And so here I need another copy of this part file, so I'll just drag off here. I need the other configuration, so I'll just select it, click Component Properties, and change it over to the short member configuration. Just like so. And it'll be a very similar process here. And so, what if you haven't caught on to it already, basically I'm going to use the coincident mate between the axes as basically the pin connections that would connect this mechanism together. And so there's one, so that aligns those holes. Again, I don't want this translation perpendicular to the front plane, and so I'll select the front plane and now this back face in order to constrain that. And so far so good, except for this motion here we really want to take control of. And so by take control of, what we're going to do is we're going to say, let's make sure that this temporary axis associated with this hole here always lies on the top plane. And so of course we can just do that with another mate, just a coincident mate there, selecting the axis and the top plane there in order to generate it. And so that allows us to fully constrain that individual component there. And so we're in good shape at this point. You can always play around with it, and I would encourage you to actually play around with the model before you get it complete. It's one of those things you don't want to have built the entire mechanism and then have it not function. And so I would strongly suggest, as you put in a couple of components there, that you grab a hold of some stuff and see if it's working the way you want it to. Because I'll say this probably more than once in this video, if it's not working correctly in this model tab, it's not going to be working correctly in the motion study tab there. And so it's much easier to figure things out in the model and then have things run a little bit smoother in motion, as opposed to having compounding problems basically then inside of the motion study. And so we need to put it in this lower half link here. And so I'll just select off of it at that point. At this point we'll basically be replicating the same mates as we did at the top side there. And so I'll go through this relatively quickly. We'll use temporary axis here to temporary axis here to make that pin connection. I'll use temporary axis here and temporary axis here to make another pin connection there. And then what's left is this translation here. And so, as usual, I'll use a face and the front plane in order to take care of that. And so now, when I go to move this thing, you can see it has the correct motion for us. And so, without considering the slider, we've got everything to the left of the fixed pin connection already in place. And so I'll put the sliders in last, and so let's work on these other longer links off to the right hand side. And so again, it's going to be a very similar process here. If I want, I can kind of pull the front plane out so I can see it a little better. We'll mate pin connection to pin connection here. by making the axes coincident. Go front plane to that face there to kill that translation. And then this axis here is always going to lie on that top plane there. Those axes of those holes are always going to be right horizontal for us. And so again, you can see the motion start to take place. And we'll do one more here. And so axis to axis, making them coincident. Same thing with these two here. And then at this point we'll grab this side of the face so we can bring it to the front side of the front plane there. So we're looking good at this point. We have 1, 2 links here. And that's this one and this one. Looks like we need one more set. And then we'll have the half-sized links next. And so let's go ahead and do that. I'll do it relatively quickly so to keep the length of this video down, because again we're just redoing the same things over and over again at this point. Alright, so there's that one, and then another one here. And so there should be all the long ones, and then we're going to basically replicate what we did on the left-hand side with the short ones here on the right-hand side. Again, always using the coincident between those temporary axes in order to mimic our pin connections. And there's the top one in place, and once more for the bottom one. Oops, I'm not in the mate. There we go. There's that. And one more. There we go. So let's go ahead and check this. I'll hide the planes, and if I grab on this side, you can see I'm getting that kind of accordion motion that I'm expecting. I guess put in the front view to check for the model. We've got 1 point here, and then we got 1, 2, 3 points to the right, 1 here, and then 3 connections to the right, so we should be good. And now we just quickly create the sliders by bringing those in. And so I'll just bring in the Lazy Tongs slider component. Here I'll move it so it looks a little bit better, because I want that to be the left-hand side one. So there we go. Go ahead and show the planes again. And so here I will go to mate as usual. Still using those temporary axes and the coincident in order to mimic those pin connections. And here I think I was thinking a little bit ahead when I created the parts. I've got this front plane right in the middle, so I can just go front plane to front plane here to center it in the Z direction, and then also I can go top plane to top plane here in order to get that in the correct orientation as well. And so that's the left one, and now for the right one. And so go mate here and here for these temporary axes, and then the planes. So again, just replicating what I did on the left-hand side. And so we'll go view, we'll turn off the planes, go ahead and turn off the axes for now as well. Both of those and the temporary axes, and give it a whirl. And so you can see at this point we're having the motion as expected, which is very good. So one thing I'm going to do is go ahead and save it. I really probably should have saved it before this point, but nothing crashed, so we're doing okay. Really, you don't want to, of course, get to the end and then have it crash and you have to start over from square one again. And so right now I've just been moving it around, obviously, to test it. But one thing you'll want to have is a predefined start point. And so by the start point, basically it's going to be the distance along the x-axis between these holes here. And so if I look right now, and if I was to go into motion study right now, my first point would be, it looks like 3.1176 inches for that center distance. And really, I'd like to control that. I'd like to start off at a nice number. The number I've picked for this is 3.75 inches. And so how do we set up that initial condition? I'm sure there's lots of different ways to do it, and one of the ways that I'm going to do it here is with just setting up a initial condition mate. And so what I'm going to do is I'm going to go from the reference geometry to a plane. I'm going to select the right plane, and then I'm going to create this plane that's offset it by 3.75 inches there. And I'm going to make sure, of course, it's on the right side of my mechanism. And so what this plane is going to allow me to do is to basically set up a specific distance between these holes as my start point. And so here, I'm going to go ahead and just rename this plane. I'll call it the initial plane here. And then what I'm also going to do is I'm going to bring back those temporary axes. And I'm going to create one more mate, and it's going to be between this plane and that axis. And so I'm just saying, hey, make sure that this plane and axes are coincident. I can check my logic here, because now if I go back and measure, the horizontal distance between these holes should be exactly 3.75 inches, which is great. Okay, so the only problem at this point is I can't move my mechanism anymore, right? If I try to grab a hold of a part, it's going to say, hey, the part's fully defined, it cannot be moved. And so we need to fix that portion of it. And so we'll actually fix that portion when we get inside of the motion study. So on this side of it, what I'll do is I'll go down to mates, though, and make it a little bit easier for me in the future here. And so you can see all these mates right now are coincidents. You could have a mixture of coincident mates, some width mates, parallel mates, offset mates, so on and so forth. But the idea is I would like the one mate that I want to be able to suppress in SolidWorks Motion to stand out from all the rest. And so the way I'm going to do that is I'm going to rename it. And so the last mate we made was the mate that's going to control the initial condition here. That was basically setting the axis here coincident with this initial plane. And so what I'm going to do is I'm just going to right click, go to the properties, and instead of this being coincident 36, I'm going to name it initial condition. And so now it has a very obvious name compared with all the other ones, saying, hey, this is the mate that's controlling the initial condition of this mechanism, which is exactly what I want. So at this point, everything is done for us inside of the Model tab. And so now we need to go to SolidWorks Motion. One thing you noticed I did is I kind of zoomed out a little bit here before I went to Motion Study tab, because I believe SolidWorks takes this first view when you go into Motion Study as the view that's going to reference when it starts the motion. And so unless you want to get into cameras and all that jazz, you'll really want to pay attention to that a little bit so that make sure that your mechanism stays within this window and it's not going way off to the left, the right, or up or down, and so forth. And so I'm in the motion study portion of it. But one problem is I only have two types of motion studies visible to me right now. We've got animation and basic motion. And so depending on what you're after, these might be suitable. If you're just making a video presentation of how your mechanism or how your product's going to move for, say, a presentation, that's great. You can get it by with just these types. But here we're actually after pulling data from the model itself here. So we're going to have the data go through its motion, and we're going to basically be querying the model to say, hey, what is the position, what is the velocity, what is the acceleration of a given point on the model, and expecting it to return to us some numerical data. And so we can't do that with either of these two options. And so what you have to do is you have to add in SolidWorks Motion. And so if I click the down arrow next to the options icon here, I've got add-ins. And here are all the add-ins that aren't always initially loaded with SolidWorks as soon as you start it up. And so the specific one I'm interested in is SolidWorks Motion right here. And so I'm just going to click the icon to the left there to say, hey, load in the SolidWorks Motion tools or functionality into this session of SolidWorks. And so I've got that checked. I'll hit OK, let it do its thing. And now if I recheck, I've got a third option called Motion Analysis, which is the option that I want because, again, I want to pull numerical data off of this model. And so I've got the right motion study type now, but again, my model still is frozen, if you will. It's all locked up. It doesn't have any degrees of freedom. It can't move at this point. And so you can tell that a little bit by the fact that I don't have a minus sign next to these file names. And so we said we were going to fix that once we got into motion study, and at this point is where we're going to fix it. And so we're going to scroll down to the bottom of this tree structure here, go to the mates node, stroll to the bottom of it. I've got my initial condition. There's the mate that I need to suppress, and so I'll just right click and suppress it. And so that should give us back the ability to move this model. And so you can see all of the minus signs next to all the links showing, hey, these things can move. Now, one thing that would be important for us to do is not actually move the model at this point, because remember we created that initial plane, that initial condition, to make sure that the distance between this hole and this hole was exactly 3.75 inches, so we know where we were starting from. So of course, if you suppress that mate and then go move your model, you're killing the whole point behind the initial condition there. And so we'll just have to be careful about that. And so how do we actually make the model move would be generally the next question. Well, for us, we're running kinematic analysis here. Means we're just interested in describing the motion of it. We're not really interested in the forces and torques that would actually be required to make this model move. And so here I'm just going to go to the motor icon. And so when I select the motor icon there, you can see I've got two different types to begin with, a rotary motor and a linear motor. Obviously, rotary motors cause things to spin, linear motors cause things to translate. Here I want a translation, so I'll click the linear motor there. Just working down the list of inputs here. Next, I've got the component / direction area here. And I've got to define a motor location. I've got to define a motor direction. And this last one is somewhat optional, component to move relative to. And so here, the component or motor location is going to be right here. I'll just select that inside cylindrical face associated with the slider. It's going to attach the motor to the slider. It's also trying to pre-select for me the direction I want this motor to translate in this case. And so it's picking up that axis, that temporary axis associated with that cylindrical face and saying, hey, do you want it to translate along that cylindrical axis? Here, I don't really want it to do that, so I'm going to right-click and clear. And I want this slider to move in the X direction here. And so one of the easiest ways to do that is to find an edge that's also going to be oriented in the X direction. And so I can zoom in on this slider and say that edge right there is always going to be in the X direction, which works out in this case. And so here I could change the direction if I wanted to go left or right to begin with. I'll just leave it going off to the right in this case. And it's ready for us to populate the component to move relative to field. In this case, we don't really need to populate that just because of the way this mechanism is going to work. An example of where you'd want to apply that to is if you have a hydraulic cylinder. And so think of the kind of backhoes or heavy equipment you see in construction environments there. Some of those cylinders are extending as well as rotating at the same time. When you have that kind of motion and you're applying the motor to the actual piston and rod assembly of the cylinder itself, you want it to be able to say, hey, move this relative to the body of the cylinder there. And so that way you have the correct motion going on. In this case, I don't have that kind of interaction, so I don't have to worry about it. So after that, we have to start describing how we want the motor to actually move. And so the most basic is obviously a constant speed. You say, hey, I want this thing to translate at a certain velocity in this case, and so 1 inch per second in the X direction. But here I don't want that. I need this thing to basically oscillate, and so it's going to be some sort of sinusoidal motion here that I'm after. And so for that case, I'm going to actually go down to expression. It's a little bit more complicated, and it gives you this nice dialog box here. And so here is basically SolidWorks is allowing you to define a mathematical expression for this motor. And so you can describe it in terms of its displacement, velocity, or acceleration. Here I'm just going to stick with the default displacement. And so I'm going to type in here the expression. So it'll be 2 times, and then here, just to make sure I get the syntax right, I'm going to come down the list of mathematical functions. I'm going to say, well, I want the sine of something, and I want the sine of 2 times, and here I want time. And so time is a variable. You can see if you go to variables and constants, time is the current simulation time. And I'm just going to hit delete a few times right after this. And so you notice there, before I hit delete, it was red check marked, or red cross, and then when I started deleting everything after it, it went to a green check mark there. One of the things you want to watch for is to make sure that this has a green check mark. I actually made a video prior to this and I forgot to do that, and it wouldn't run because it thought there was something off there to the right. And so that's one thing you might want to be sure to make sure is that everything after your last parenthesis there, or last characters of your expression, there's nothing extraneous sitting out there that you can't really see. And so here I just hit the delete key a few times, and it seems to make everything happy. As far as the graphs down here below, 2 times the sine of 2 times t where t is time, should be this curve right here, and then it's basically showing me also the corresponding velocity, acceleration, and jerk plots off to the right there. And so this looks good, and I'll just hit OK, and OK here as well. And so you can see now that I've got a nice yellow line showing that, hey, the linear motor is going to be active during this time frame. If you want to, you can hit the plus sign here to make the zoom of the timeline here a little bit bigger, so you can see, okay, I'm at 1 second, 2 second, 3 second, 4 seconds, okay, I have 5 seconds there. If you want to, you can select and drag this cursor back and forth here in order to define a different study duration. In this case, 5 seconds should be fine for us. Other things you can change around in the study is the frames per second value here. Basically, this is the time step for the delay between each SolidWorks calculation here. And so by leaving it at 25 frames per second, it's going to make a calculation every 1/25th of a second. And so depending on how fine a step size you need in your analysis, you may be changing that value. Other thing that you might have to do is come down to advanced options and change the integrator type. The integrator type is kind of like the solver of the motion study itself there. And so if you start getting a bunch of errors and you think you've got everything right, you may need to change the integrator type and just see if that works. In the past, I've used gstiff, and the second one, si2_gstiff, a little bit more than the wstiff there. And so just when you're troubleshooting, trying to get the solvers to work inside of the SolidWorks Motion, you may try changing the integrator type there. And so we'll just leave it at 25 frames per second for this example. You can see there's a lot of different other options you can have in setting up your studies, but for this specific example, I think that should be everything, and we'll see what happens when we hit calculate here. And so when I hit calculate, it's going to actually run the SolidWorks Motion analysis. And so it ran the solver. You did see the motion there. We'll go ahead and hit it again and see the nice motion happen there. And the little chime there that you might have heard showing that, hey, it's done. And so that's what should happen. You should be able to run the analysis. And remember, you have to calculate the solution. This is where it actually does the number crunching, whereas if you hit these buttons here, it's just playing back what it's already calculated. And so at this point, we've got the nice motion. If you want to, you can save it to a video file here, but we were after getting actual data from it. And so the way you do that is with the results and plots icon. And so I can go to results and plots. Here I've got different categories. In this case, I'm after displacement, velocity, and acceleration, so everything will be under this first category. And I want a linear displacement. And we can say X, Y, or Z. Here, X or magnitude would be the same value since I've only got one-dimensional motion here. We'll just go X here. And one thing I can do is, say, select this edge here and this edge here. And it should report the data for me. And so you can see the data here. It starts off roughly negative 11 inches apart and then gets to a close value of roughly 5 inches. And then on the far end, it's roughly 17 inches away from that fixed pivot connection there. And so here we're talking about the distances between this point and this point here, or the displacement between those points, seeing as we just have one-dimensional motion there. And we're just talking about the X displacement there. So next thing we would want to do is show the velocity and acceleration. Really, they're the same processes here. And so here I just go to the category that I want, spec out the quantity that I want. If I need to, I can spec a specific component. Here I'll just do magnitude. Let's keep going with X component there so we can get the positive and negative side of things here. And so there is the velocity curve. And so you can see the max velocity is roughly 12 inches per second. And finally the acceleration. And so again, I'll go to results plots, velocity and acceleration, we'll go linear acceleration, we'll go X component, and select here and here. And there is the acceleration of these points. Notice the first point that I'm picking has no translation at all, so these should be the absolute velocities and acceleration, and it should not have to be a relative one. And so one thing you notice, you can actually flip these plots a little bit. I've always been selecting the fixed point and then the point on the slider. Notice the plot here, the way it looks. And then one thing I can do is change that a little bit. If I reverse the order that I do my picking in, I'll pick this one and then this one, and then show the plot. We have the exact opposite here. Before it went something like this, went down before it went up. Now it's going up before it goes down. And so I'll just be consistent here and make sure that I'm selecting this point and then this point. Just as a matter of really sign in this case. And so you just have to possibly check that in order to make them match up with your hand calculations there. And so we've generated all the plots. So if you want to, you can show them all at once. If you just right click and go show all plots. You can also rename them if you'd like, instead of having plot 1, plot 2, and plot 3 there. And so this looks like a good stopping point for this video. I've created displacement, velocity, and acceleration plots of the point that we're interested in predicting the output motion of. And so in another video, we'll basically take these plots, bring them into Excel, and see how they compare to our theoretical solutions. So thank you for watching the video.